Anyone who would like to answer these questions? The first one, it's related to energy conservation, and you have a bunch of situations and you're supposed to answer a bunch of questions regarding them. So the first one is an elevator moving upward at a constant speed. Okay, for these situations, you're supposed to draw a pictorial representation. You're supposed to label displacement vector. You're supposed to draw a free body diagram and show all the forces that acts on that elevator, and then you're supposed to make a table of work done by all forces, net work, and the change in kinetic energy. So we have 5 different situations, and for each situation we are supposed to answer each one of these questions. So the first one is trivial. It's just an elevator moving upward at a constant speed. So let this be the elevator, and it's moving upward at a constant speed, and after some time, since we have been asked to show it pictorially, so this is how you can represent it. So this is the initial state, this is the final state. Next, you have been asked to draw displacement vector. So displacement vector is easy, so you pick an axis, which generally a good choice is to pick it at the center of the elevator. I mean, you can pick any point, you can pick bottom, then your displacement vector should be from bottom to bottom of this picture to the bottom of this one. I just picked the midpoint. And so this arrow would be your displacement vector R. You can represent it with delta R, doesn't really matter. Okay, this answers first 2 questions. Third one is free body diagram. Free body diagram, we don't need to show the elevator. We just represent elevator with this one point, and then we have been asked to show all the force. Actually, that is part of free body diagram. You represent the entire object by a point, and then you represent all the forces acting on that point. Okay, so since the elevator is moving upward at a constant speed, and elevator moves upward because there's a spring pulling it in the upward direction. And if the speed is constant, it means there's no acceleration, there's no net force, and so the tension that acts in the upward direction, this should be balanced by the weight of the elevator, which acts in the downward direction. So this is free body diagram. And now the interesting question, the third one, fourth one. We are supposed to answer to the question that how much work each of these 2 forces do, and then we are supposed to calculate the net work and then the change in kinetic energy. Okay, so in order to calculate work, we know the formula for work is a force dotted with the displacement. Okay, and you are just supposed to answer whether the work done by each force is positive or negative. Okay, you can calculate the numerical value, it wouldn't really matter, but for this question you are only supposed to answer whether the work done is positive or negative. Okay, and the positive and negative that lies in this dot, it's not an ordinary multiplication, it's a dot product. Okay, and if you expand this dot product, this gives you the magnitude of force times the magnitude of displacement times cosine of angle between force and displacement. Okay, so you can see here, if you consider tension force, which means if you want to calculate the work done by tension force, then you have F replaced by T. D would be the displacement of this elevator, which we have represented by R in going from this point to this point. And the main thing which will tell you whether the work is positive or negative is cosine of angle theta, because cosine theta can have positive as well as negative value. So you just need to look for the angle between tension and the displacement. Okay, so if you look at tension, it acts in the upward direction, and the elevator also moves in the upward direction, which means the tension vector and the displacement vector, they are in the same direction. When two vectors are in the same direction, the angle is 0, and cosine 0 is plus 1, and so this entire right hand side, it gives you plus 1. You can calculate the numerical answer. If T is the tension and R is the displacement, then the work done would be T times R, and this is positive. Okay, so this is what you are supposed to answer. Now for the work done by the other force, which is the force of weight, let me represent it with WW. And this will be, again, you look at the direction of weight, in which direction the weight is acting, and in which direction the elevator is moving. So elevator is moving in the upward direction, but the weight acts in the downward direction. When two vectors are in the opposite direction, the angle between them is 180 degrees, and cosine of 180 degrees is minus 1. And so you see, when these force and displacement, they are multiplied with the negative 1, you get negative times that magnitude. And so in this case, if W is the weight of the elevator and R is the displacement, this work will be negative, because we have cosine 180 equals minus 1. And so this is the work done by the weight and tension force. This gives you the individual works done by the forces. You are also supposed to calculate the net work, which is the total work. So W total will be the sum of work done by the individual forces. So it will be W T plus WW, and it's 0. So previously we were only supposed to answer whether it's positive or negative, but here you see we can also show that their magnitudes are also equal. And why their magnitudes are equal? This R displacement is the same in both cases. So we need to show that T is equal to weight of the elevator. And how do we show that? You use Newton's second law, summation F equals mass times acceleration, and summation F is the total number of forces acting on the system. So we have tension force, which has positive magnitude because it acts in the upward direction. We have weight, which acts in the opposite direction, so with a negative sign, and we know that the system or the elevator moves with a constant speed, which means that the net acceleration is 0, because acceleration is defined as change in speed or velocity. And so from here we immediately see that T equals weight of the elevator. And once we have this one, you can see that if I substitute T equals W, then both works. For tension force it becomes W times R, and for weight it becomes minus W times R. And so this equation gives you 0. So net work is 0. Net work is the sum of work done by all the individual forces. And finally, you're supposed to calculate the change in kinetic energy, and that comes through work energy principle, which tells you that the change in kinetic energy, delta K, is equal to the total work done by the system, or the net work that I have calculated here. And I have calculated Wt to be 0, so change in kinetic energy should be 0. And this answers all the questions. Can anybody tell me if you can arrive at the change in kinetic energy that it's 0 by any other argument without going through all these steps? Can you figure it out? Just from the statement of the problem, can you tell that the change in kinetic energy would be 0? You should be able to tell that. You see, here I have calculated it, and in order to show that it's 0, I had to go through all these steps, because this is the eventual results of going through all those steps. But I'm claiming that you can just answer for change in kinetic energy from the statement of the problem. Can anybody argue that from the statement of the problem that the elevator moves upward at a constant speed? This tells us that the change in kinetic energy should be 0. Yes, Shanaz.
Is it constant speed?
It's constant speed. Correct. You see, these things help if you just read it carefully. These things help on your exam. For example, if you have such kind of problem and you see that the only thing that you need to answer is to tell what will be the change in kinetic energy. And you know this method and you're like, okay, I have to go through all those steps. But if you know that the since speed is constant and changes kinetic energy is just the final kinetic energy minus initial kinetic energy, and you immediately realize that the change in kinetic energy should be zero. And now then you can go the other way around. You can use the reverse gear, and now you have arrived at your final result. And then you arguing and start going in the backward direction. And you're like, since my change in kinetic energy is zero, okay, then the total work done by the system should be zero. And once you arrive at this result that the total work is zero, you immediately realize that if one force is doing positive work, the other one should be doing negative work, and you don't need to do all this mathematics. You can just argue your way back. Different way of looking at the same problem. Okay, the second situation is an elevator, a descending elevator breaks to a halt. So elevator is initially descending. We assume that it's descending at a constant speed, and then you apply the brakes and it stops eventually. Okay, so our situation is just like that, but in this case, since it's descending, so let me start here, and I'm just gonna go, the same diagram would hold for the first part, just the arrows will change their direction. So this will be the initial state, this will be the final state since they are descending, and that displacement vector will be in the downward direction. So I'm gonna go to this part. So it's descending, and let's assume that that's the point when it's descending at constant speed, and then you apply the brakes and it comes to a halt, and let this be the displacement or the distance in which it comes to a halt. So at this point it stops. Okay, so this is your displacement vector. You can represent it with R or D or whatever you want, but its direction is down. Okay, so the only force that acts here is the force that stops the elevator. And since we know that the elevator is supported by some spring in the upward direction, so let's assume that it's the frictional force that acts between the springs and the pulleys. Okay, so we have some force that is acting in the upward direction. Let me call it small f. Okay, under the action of this force, the elevator stops. And you immediately see that the work done by this force will be negative. Why it's negative? It's simple. Elevator is moving in the downward direction, and if you want to stop it, you have to apply force in the opposite direction. It's just like you are trying to stop your friend who is running towards you. If you have to stop it, you have to apply force in the opposite direction in which he is running. Okay, and so the work done will be negative. It will be minus f times d. D is the distance, this one, magnitude in which it stops. F is the force, and the negative sign came from this argument. Since force and displacement are in the opposite direction, so cosine 180 is minus 1, and so you have the negative sign. Now from that one, so there was only one force in that problem, because we are only supposed to deal with the situation in which the brakes are applied and the elevator comes to a halt. We are not worried about what was the initial state of the elevator. So you have only one force, and the work done by that force is negative. Okay, and this immediately tells you, since this is the only work, that net work will be negative. So this will also be equal to W total. And from here, now you immediately see that change in kinetic energy is equal to W total. And so change in kinetic energy will be minus delta K, or minus F dot D. That's it. That's the solution to your problem. Let's again go back and try to see if we can get the answer for the change in kinetic energy from the situation of the problem. Like, can you figure out that the change in kinetic energy would be negative from the statement of the problem that the elevator brakes are applied and elevator comes to halt? The same argument. In the previous case, you had an elevator ascending at a constant speed. So speed was constant, which means initial and final speeds were same. and so the change in kinetic energy was same. But in this case, elevator comes to a halt, so final speed is 0, and initially it had some non-zero positive speed. So it has initial kinetic energy non-zero, final kinetic energy 0, and when you take their difference, like you calculate the change in kinetic energy, it's a final kinetic energy. So change in kinetic energy is final kinetic energy minus initial kinetic energy. Final is 0 because the elevator comes to a halt, and initial has some positive value, let's call it ki, and so your answer should be minus ki. So your change in kinetic energy, delta K, it is negative, and that's why I had this negative sign. So you can argue backward and forward whichever way you prefer, both are equally valid. Sometimes it's easier to immediately guess the change in kinetic energy from the situation or statement of the problem, and then it becomes even easier to go the backward way. Once you find the change in kinetic energy, you can immediately realize that this is equal to the total work, and if total work is positive or negative, you will immediately realize that whatever force I have, if it's one force, then you know that that's the work that that force does, whether it's positive or negative. So you should have both tools in your kit. In order you get stuck on one way, you should be able to do the same thing by going the other way. Okay, the third one is a box slides down a frictionless slope. So we have situation, we have a slope, and we have a box on top of it, and the surfaces, the friction is 0 between the surface of the slope and the box. So let's let this be the slope, and this is the ground, and it makes some angle, let's call it theta, with the ground, and then we have a box here. Okay, if you wish, you can again represent it with a point, wouldn't really matter, but I'm just going to show a box, and next we can show the forces on it. So this is the direction in which the weight of the box act, and then we can resolve this weight into two components, one perpendicular to the this slope and the other one parallel to the slope. And since this box is sliding in this direction, you immediately see that this component of W, which is W sine theta, this is responsible for the motion. So this is the force which is acting in this direction and causing this box to slide. Okay, so let's try to answer. So this is the pictorial representation, and then you say that box initially starts at this point and ends up at this point. So this is the final location of the box, and then you're like, okay, it started from this point and ended up at this point. This is the displacement vector. So this is displacement vector D, or I have used the symbol R previously, so whatever you prefer. So this answers the first two questions, and the third one is when you represent these forces. That's a free body diagram. And now you immediately see that there is only one force. There are two forces. So let's calculate the work by both forces. What two forces? One force is W sine theta, which is causing the box to slide downward, and the other one is this one, which is W sine theta. And then we have a normal force in this direction. Okay, so there are three forces. But why I was saying there is only one force, because there is only one force which does some non-zero work. The normal force and the force W cosine theta, they perform no work. So this is W cosine theta. Okay, so let's calculate the work by all these three forces. So work done by the normal force, this will be F dot D, and F is normal force and D is the displacement. Now it's magnitude because I'm introducing the angle theta. Okay, let me call this the angle phi. This angle is different from this angle. Why? This is the angle that this inclined plane makes with the ground. Okay, this is the angle which normal force makes with the displacement vector. Be very careful about these things. When you calculate the work done by a force, that I have used this formula, W equals force dotted with displacement. This dot product gives you force magnitude, displacement magnitude times cosine of angle, let me name it alpha. This angle which comes in the definition of force, this is the angle between these two quantities. Okay, so this angle that I have defined here, it's totally different angle. When you calculate work, you always find the angle which exists between these two quantities, force and displacement. I'm choosing alpha, phi, beta, whatever. Name doesn't matter. The thing that you need to remember that this angle which comes here with cosine theta, this is the angle which exists between these two quantities, between force and displacement. Now, we have normal force here. Force is normal force, and this is the arrow which represents normal force. And this is the arrow which represents displacement, and this is the angle. This is the angle which I have defined as alpha, and you can see this is 90 degrees because they are perpendicular to each other. And cosine 90 is 0. So the work done by the normal force, since cosine 90 is 0, so everything becomes 0, and work done by the normal force is 0. Okay. Now let's look at the work done by this force, which is W cosine theta. So now work done by the let me actually name it W cosine theta, and this again will be F dot D. What is F in this case? It's W cosine theta. So this will be W cosine theta. This is our force. D is our displacement, and then we have cosine of angle alpha. This alpha may or may not be equal to this alpha. So I'm gonna change the name. I'm gonna call it alpha prime so that you're not confused by the same name. What is alpha prime in this case? Look, W cosine theta, it's directed in the downward direction. This is the vector D, it's directed in this direction. And now my alpha prime in this case, it's this angle between this green line or this line and this line. Okay, and this is again 90. And this, so cosine alpha prime, this becomes cosine 90 degree, and again cosine 90 is 0, and so everything this goes to 0. And so work done by this force, W of W cosine theta, this is 0. Now we have one more force, this force, W sine theta. Okay, so the work done by W sine theta, this is the force, and so work done by this force. General formula is F dot D, which becomes F D cosine of, let me call this angle beta. So in this case our F is W sine theta, D is this displacement, it's the magnitude, and cosine beta, cosine, and now we need to find beta. So beta is the angle between this force and this displacement. So this is W sine theta, and it's directed, let me use a different color, it's directed in this direction. This is our displacement vector, it's also directed in this direction, and you see both of these red arrows, they are parallel to each other. And when two vector quantities are parallel to each other, the angle between them is 0 degrees. And so this beta is 0 degrees, and you get cosine of 0 degrees. And cosine 0 is 1, so the work becomes W D sine theta, which is positive. Okay, so you can only guess from here that the work done is positive. Okay, if you want to calculate the exact value of work, you need to know the weight of the box, the displacement which it slides down the inclined plane, and also you need this angle, the angle which inclined plane makes with the ground. But since you have not been given with any of these numeric values of any of these quantities, So you only can guess that the work done will be positive, and that's precisely what have been asked in the question, whether the work done is positive or negative. Okay, so you know that the work done is positive. But always remember that this angle is very important. It's the angle between force and displacement. Any other angle shows up, just let it be there. Okay, so we have positive work. Net work will be positive because net work will be the sum of this and that, and these two are zero, so net work will be positive, and so change in kinetic energy will be positive. So W total is positive, which means it's greater than zero, and this gives you change in kinetic energy is greater than zero. This tells you final kinetic energy is greater than initial kinetic energy. Can you guess that the final, like again, let's go back and ask the same question. Can we guess from the statement of the problem that the change in kinetic energy would be positive? Can you look at that diagram, or from your experience, can you tell that the total kinetic energy will be positive, which means the final kinetic energy would be greater than the initial kinetic energy without going through all these calculations? Can you guess? Let's not talk about inclined plane. If I drop this marker here, do you know that its speed increases as it goes down? And that's exactly the same situation. It just does it in that situation. It wouldn't increase at the rate in which you just drop it downward. And so you could have guessed that the change in kinetic energy would be positive, and from there you can immediately guess that the net work done will be positive. And once net work done will be positive, you immediately know that this is the only force which is doing positive work, and the other two forces are doing negative work. You see, so in all these situations, if you go backward, that's easier for you to get to the right answer if you, rather than if you go in the standard way and go through all this mathematics. Okay, so you should know all these things so that whatever you feel like doing, you go through that path. We have two more situations. I'm gonna leave them for you, and I'm gonna go move to the next problem. Work done by a variable force, the second problem. That's easy. I'm just gonna go solve the first part, and we have a graph, and we see that the graph has some inclined or like some kind of shape, and we are supposed to calculate the work done. So the first diagram is, we have a displacement and force graph, and the force varies somewhat like this. This is on the x-axis in meters 6, this is 0, and the maximum force is on the force axis in newtons 10. Okay, so you're supposed to calculate the work done. So when you have a graph between force and displacement, the work done is simply defined as the area under the force displacement graph. What is the area under this graph? So this is our graph, and this is the area under this graph. So if you somehow find the area of this region, that's your work done. So in this case, the work done is area under the curve. How do you find the area under the curve? You see the shape is triangle, and the area of a triangle is 1/2 times base. This is the base of this triangle times height, and this is the height of the triangle, and the area under the curve, which is equal to work done. For a triangle, it's 1/2 multiplied by base multiplied by height. And so 1/2 base is 6 meters, height is 10 newtons, so it's 6 multiplied by 10, which turns out to be 30 Newton meter, which is joule. So the work done will be 30 joule. In the second diagram, you have two regions. Okay, you have two rectangles. Rectangle is simply length multiplied by width. That gives the area of the rectangle. For this upper part, the area will be positive because force is positive. For the other rectangle, since force is negative, so area will be negative. So you add both of them, which will be subtracting them, and you get the area under the curve, and so is the work done. I will not be doing fourth one, but I'm gonna do the third one, and this is related to potential energy. And this asks for a question in which you are supposed to answer certain questions which relate the force and potential energy. We have a curve, and you need to know this relation: partial u divided by partial x. This right hand side is the change in potential energy with respect to displacement, and this ratio gives you force, and this quantity is also called slope. So it's minus slope of potential energy with respect to x. This is useful when you have a graphical representation of potential energy and displacement, and you are supposed to calculate force. Okay, so you just look at the regions of this graph. So I'm gonna quickly try and plot this graph because it's important, and the graph is somewhat like this. Okay, and this is our 0, x is 0, and then maximum it goes up to 10. Okay, so this is slope. You are supposed to answer questions, and the first one is in which interval of x the force on the particle is towards right. Towards right means positive. And similarly, you are also supposed to answer in which interval the force is towards left, which means the negative force. So here, look at this equation. The regions in which slope is positive, the negative sign with multiplied with the positive gives you a negative, and so you get the negative force. And the regions in which slope is negative, you get a positive force, because negative multiplied by negative will be positive. So you just look at this graph, and you need to pick those points where slope is positive or negative. So the graph moves towards right. So this region, starting from this point until this point, this is the region in which slope is positive, greater than 0. And so in this region, the force will be negative, less than 0, or the force will be towards left. Starting from this point up until this point, the slope is positive. In this region, the slope is negative, because if you take this point, this will be your line, and on this line, this is your final point, this is your initial point. And so you see the initial point has more potential energy compared to final point. In this region, your slope is positive, and if slope is positive, this tells you that your force should be negative, which means less than 0, which means it will be pointed towards left, and so this will be positive. Again, starting from this point until this point, this region, slope is negative, and so force will be positive. And from this region until this region, this is slope is positive, and so force will be negative. Do you have question regarding this? This might be confusing for you. You know how to calculate slope of a line. You pick a point. For example, if I want to calculate slope at this point, so you draw a line, a tangent line. You draw a tangent line, and on that line you pick 2 points. Let this be initial point and this be final point. And then you see that the potential energy corresponds to initial point, have some value which is less than the value at this point. And so the slope of potential energy, which is slope equals uf minus ui divided by xf minus xi. So this is xi, this is xf. Xf is greater than xi, so your denominator is positive. Uf is greater than ui, your numerator is positive, and so your slope is positive. Okay, and that's why I wrote here that in this region, starting from this point up until this point, slope is positive, and if slope is positive, this negative sign tells you that the force will be negative. So you are supposed to tell the region. So this region, slope is negative, force positive. Then this region, slope is positive, force is negative. Again, slope negative, force positive. And in this region, slope is positive and force is negative again. Okay.